Lab number 2 deals with operational amplifiers. As you may recall from ECE 201, 202, and 203, we talked about an ideal op-amp in various configurations. The inverting amplifier that we talked about previously is actually shown here on page 1. One of the properties we had for ideal op-amps is that if there is feedback from the output to the input, we're going to assume that the circuit's stable, and that'll force the voltage across these terminals to shrink to 0. So we could label that on our op-amp, no voltage and no current. If we apply a voltage, most likely a current will flow. We could just pick a direction, call that I1, and maybe call this current I2. What I want to solve for is V out in terms of V sub S. Rise in voltage would have to equal the drops around the loop, and so that's going to be I1 times R1 plus 0, and that's this equation right here. We're going to solve for I1, and that would be V sub S divided by R1. Okay, so I've got the current I1 in terms of V sub S, but I really want V out in terms of V sub S. So let's look for a second loop here. It's a closed path starting at ground, coming back to ground. So the rise in voltage is 0. There's a drop of I2 R2 plus a drop of V out. So V out is a negative I2 R2. But the current I1, because nothing goes in the op-amp, is equal to I2. So substituting that back in, this equation, we then have minus I1 R1, but then I1 is V sub S over R1. So then dividing by V sub S, we wind up that the gain is equal to minus R2 over R1. Now, as we've seen in our previous courses, this inverting op-amp is a very common building block. In fact, we're going to use it in quite a few experiments to make a variety of things. So modeling this would allow us to not have to keep rederiving all the equations again. It's also helpful in a design sense. All right, a model is really a circuit that has exactly the same equations as another circuit. What I'm interested here is the output, the input pins, and the output pins. The current I know coming in here from the last page is V sub S over R1. And I know that the output here is a minus R2 over R1 times V sub S. What's the current coming out of here? Well, between these two terminals, here and here, back through the op-amp, there's actually a voltage-controlled voltage source, so really infinite gain times a 0 voltage across here. Well, it's kind of a strange element. It's still a voltage source, and so any load you put here won't change the value of the voltage. But back in the 201 notes, I actually derived an expression for the output resistance looking back in a little bit more formally. This is, I call, more of a seat of the pants argument, where I'm just going to use some simple principles to argue why something's true. Can I make up a circuit that does all of these things? Well, this looks like Ohm's law. We're saying that the voltage equals the current times the resistance. So if you apply a voltage and that current flows in here, then just putting a resistor here will create the same effect. The output is equal to the input times a gain of minus R2 over R1. You could leave the minus sign here, or you could put the minus sign right here. Then the 0 Thevenin resistance means you can put any load you want here, except a short circuit. Second very commonly used amplifier is called a non-inverting amplifier. Here too we have some form of feedback between the output and the input. We'll learn in later courses about positive feedback and negative feedback. Some books claim that all positive feedback is unstable, but we'll show that that's not really the case. But let's leave that for another course. So we do have feedback, and we're going to assume that it is stable, and therefore the voltage across these terminals is forced or shrinks to 0. So let's label that no voltage. Again, the current is 0 because the resistance is very high. The voltage across this resistor here, because the current in this resistor is the same as R2, there's nothing here, we could use the voltage divider rule, so that the voltage across these two resistors is divided up with R1, which is over here, over R1 plus R2 times the voltage that's across those two resistances. If you go around this loop, the rise in voltage equals the drops, and so V sub S equals V sub N. So plugging that back over here, we get that V sub S is equal then to V out R1 over R1 plus R2. So if we solve for V out, divide by V sub S, take the reciprocal of this, we get this expression, or you could write it as 1 plus R2 over R1. The reason it's called a non-inverting amplifier is that the gain here is positive, but it's really, once you've looked at the inverting, that would make sense. So the inverting amplifier had a minus sign. That just means that if you had a sine wave input, the minus sign would flip it over, it would invert it. Same is true for any other wave shape. Here too, let's try to model this because it is a commonly used element. What do we know? The current coming in here is 0 because it's the lead of the op amp. The output is a multiple of the input with this positive value. And lastly, we have a low impedance voltage source between these two terminals, so our Thevenin resistance is 0. And again, it means you can hook up any load you want here and the voltage won't change. So to build that into a model, all we really need to do is use a voltage-controlled voltage source with a gain of 1 plus R2 over R1. We've got a model for the circuit. Again, our labs will have concepts that are covered and laboratory techniques associated with each one of them. We're looking again at accuracy of components and instruments as we work through some of the material in the lab exercise. We just talked about the properties of an ideal op amp and then the inverting and non-inverting configurations. In lab, we'll review doing true RMS voltage measurement using the digital multimeter and then using the dual trace feature in the scope to be able to measure gain and phase angle. And this is lab number 2.